This is lab 3, magnetic fields of permanent dipole magnets. So this lab had 3 parts. First, we conducted an experiment where we measured the distance dependence of the magnetic field due to a small bar magnet. Then we created a model to demonstrate this experiment. And then we compared the results from our measurements to the output of this model we created using the equations derived from the Biot-Savart law. So there are some fundamental principles needed to understand this lab. The first is the Biot-Savart law, which describes the magnetic field produced by a point charge and is stated there. Next is the magnetic field due to a dipole moment. Now, this is derived from the Biot-Savart law, but there's 2 cases. First is when your observation location is perpendicular to the magnetic dipole. In this case, your magnitude of the magnetic field is proportional to the mu, or the magnetic dipole moment, and inversely proportional to the observation distance cubed. The second case is when your observation location is on axis to the magnetic dipole. In this case, the value of the magnetic field is 2 times the magnetic dipole moment, is proportional to that, and is inversely proportional to the observation distance cubed. Next is Earth's magnetic field. The Earth does have a magnetic field that can affect magnetometer readings. Now, by measuring orthogonal to Earth's magnetic field, meaning that we had an initial x component of 0, this was accounted for. Now for the experiment. This experiment had 2 parts. In the first part, we used a magnetometer to measure the distance that experienced a specific magnetic field in the x direction of a bar magnet on axis. Now we were looking for what distances achieved specific magnetic fields from 20 microtesla all the way to 220 microtesla. In the second part of the experiment, we measured the off-axis magnetic fields along the 45-degree axis. Now, as you can see in the diagram, that's how we placed the magnetometer, and that's how we measured the distance. So from that experiment, we gathered a lot of data. Table 1 is the distance magnetic field relation data, and as you can see, as distance decreases, average magnetic field magnitude increases. Graph 1 is the data from Table 1 linearized and plotted. We're going to use that information later. And Table 2 is the 45-degree axis field data. We used an average distance perpendicular of 0.19 meters, which translated to a distance of 0.27 meters, and got us an average magnetic field net of 5.65 times 10 to the negative 5 Tesla. So using that data we collected, we did some analysis. We used the natural log to linearize the data from Table 1 and found n to be the slope, which was the distance factor. This was equal to about negative 2.7. Now, by using the natural log of k, we could calculate mu, or the magnetic dipole moment. This came out to be 3.84 amps per meter squared. So this is the code for my model. First and most important is the observed constants. Here we have mass, charge on each of the tapes, distance of the top tape floated, and chargeable proton, and gravitational force. The most important part of this code is in this while loop. Now the object of this model is to figure out the amount of charge necessary on one piece of tape to float the top tape above the bottom tape by the measured distance of 0.018 meters. Now, this while loop does just that using Newton's second law. It runs as long as the magnitude of the known gravitational force is greater than the magnitude of the calculated electrical force. Now, when this model runs the first time, the magnitude of the electrical force is going to be much smaller than the magnitude of the gravitational force. So what we're going to do is that each time this while loop runs, we increment the charge in order to get as close to that gravitational force as we possibly can. Now, when we run this program,
the dipole B function. This function takes 2
we can see that we do get really close to that gravitational force. And we find that our charge is different than the one that we calculated with our other model
our model that
the
treated the
magnetic
tape as a
field of
point
6
charge.
observation
Here on
points
this
of
model,
this
you
bar
can
magnet.
see that there's a
We
lot of
have
green arrows,
2
and that
observation
represents
points that are
the
on
electric
axis and
force
4
on each
observation points that
individual
are
segment
perpendicular to the bar
of
magnet.
that
And
piece of
so
tape that
you'll
we've
see
broken
that
up.
once I run this code and the
And then
model
the white
displays.
arrow
Now, the
represents
second part of
the
this lab
electric
was
force on the
to
tape,
demonstrate
and
the
the yellow
magnetic
arrow
field
represents
45
the
degrees
gravitational
off-axis from
force.
the bar magnet. So
to process all the information from that lab, first we're going to compare the 45-degree axis magnetic field measurements. The measured magnitude was 5.4 times 10 to the negative 5 Tesla, and the calculated magnitude was 2.896 times 10 to the negative 5 Tesla. They are quite different, though they are in the same order of magnitude. Now, the next question was, what if you hadn't oriented your experiment to compensate for magnetic north? Then the results would have been inaccurate. The measurements would sum the magnetic field from the Earth plus the magnetic field from the magnet, and that wouldn't be correct. Next, the question was, what if you stick 2 identical magnets together end to end and run the experiment again? In this case, all the measured values would double, since there would be 2 times the magnets and 2 times magnetic field. The magnetic dipole moment would double, and the observed magnetic field would double.